Okay. So apparently PowerPoint is crashing today. Just a moment, as we're trying to fix that. Okay. I think I better do it now. Okay, I'll do it from my laptop then. All right. So yeah, as I was saying before, I was kindly interrupted. The goal about today is understand the various LLM. Okay. Sorry. Okay, let's try and do it this way. Okay. Okay now. Also online. Okay, now let's try and work with that. Okay. So okay. So the first question is, what's an LLM? Effectively, LLM, you can think of it as a black box. You have some input, you give it some input, some prompt, some text, for example, and then the LLM will just give you some output, effectively serving your what you ask for it. So the LLMs are not deterministic. So for the same question, there is a different probability of getting a different answer every time you ask it, and so on. But you can use it for many tasks. You can use it for either conversing, providing some translation, Q&A, classify some text, providing some summaries, transcribing videos, text generation, and so on and so on. The idea is that there are various popular LLM models there, some foundational models. So for example, I'm pretty sure you all know ChatGPT, Gemini, Claude, Mistral, and so on. So they have different characteristics. So they have different sizes. For example, ChatGPT-4 was estimated to be roughly 1 or 2 trillion parameters, between 1 and 2 trillion parameters. Gemini in the order of 120 billion parameters, Claude into 200, and so on. And each one, if you happen to use all of them, you can see that they have different strengths and weaknesses. So, and some they can provide some multimodal and code capabilities better than others, for example. Some others they can provide some better reasoning, and so on. The first three in this table are effectively, okay, sorry. The first three are, these are owned by, these are proprietary to OpenAI, to Google, to Anthropic, and so on. The other three, the difference is that they are open source. Okay, so actually you can take the weights and you can use them from wherever you want. And these are usually used for fine-tuning third-party models and so on, right? And then we also have some specialized LLM models. For example, we have one called LLM. This is in the size of 9 billion parameters. This was trained from scratch by the European Union. And the goal of that is to provide multilingual EU languages and translation. We also have Cricri and Meltemi. These are fine-tuned versions of Llama 3.1 and Mistral. And they are towards providing, these are Greek LLMs, for example, that you can use and converse in Greek and so on. Then you have CodeStral. This is a fine-tuned version of Mistral 22 billion parameters. So this is an LLM that is specialized in code generation, for example. And then you have MedGemma. This is a fine-tuned version of Gemma 3. And the idea of that one is to provide some specialized knowledge in the medical domain and so on. So we have the foundational models. These are very good in general tasks and so on. And then you can also have some specialized LLM models that were either fine-tuned or created from scratch. Now, the first session is about local LLM deployment. And the question is it even hard? I mean, don't you just use the OpenAI API if you have used it in the past? And, well, sort of. Yes, but no. Okay. The idea is that you have this abstraction. You have the user, you send your request, then you ping some server, let's say the OpenAI server, and then you get the response back. Conceptually, that's just it. But in doing so, there are some intricacies that you need to deal with. So, for example, the first question is, what models are you going to use, right? So you have mainly hosted APIs that they have mainly proprietary models, and then you can have self-hosted APIs that you have open source models and so on. And this varies in where they are deployed. For example, the hosted APIs are usually by some third-party provider. So you have OpenAI, you have Anthropic, Databricks, and so on. And then you can have the self-hosted open source LLMs, for example, that are hosted on Hugging Face, or you can get other models as well and host them on your own machines. But why would you want to self-host yourself? And the answer to that is that there are many reasons. So in the long run, you provide, as you use more and more the models, the costs are sort of plateau at some point on the equipment cost and the maintenance cost. Although if you're using OpenAI, for example, the costs are always scale with the usage. And you can get better performance, actually, depending on the task. You can use fine-tuned models, for example, if your task is, if you want to use code generation and so on, right? And then you have the privacy and security issues as well, because if you host the local LLM, if you host the LLM locally, then you don't provide any data to a third party and so on. And many enterprises, they care about open source for many reasons. The main ones are the cost, the customizability, you have the flexibility to select your own LLM and so on, and control. So it makes sense if your concern is security to self-host, but the question is how much really harder is than using the OpenAI API. And the answer is it's much harder, actually, because you have to deal with a few things that are not very straightforward. Models are large, and the size of models is still increasing, and so on. On the other side, GPU prices are super expensive. If you want to buy one H200, you be prepared to pay 30 to 35,000 euros, okay, just for one GPU. And the field is still evolving, and it's evolving quite fast, right? And these are the three main reasons that the three main issues that you have to deal when you want to host centrally and locally. But there are actually some tips on how you can make this deployment less painful. For example, you need to know your deployment boundaries. So first, you need to know the latency requirements, how much time you want to wait from the time you send the prompt until you get the response, for example. How many users are expected to use the system, either asynchronously or at the same time, and what hardware you have available to you. Do you have any GPUs at all? Do you have powerful GPUs? Do you have one GPU, 4 GPUs, 100 GPUs? And this one, these three requirements change your boundaries quite a lot. The other thing is that you should always quantize your models. So instead of using all 16 bits or all 32 bits, let's say, for the model weights, you can use 16, 8, 4, or even 4 bits for each weight. And this actually increases the performance of the model without sacrificing a lot of the accuracy. And the main idea is that you should start with the available infrastructure and then work backwards. So if you have, let's say, one GPU card that has 40 gigabytes of available memory, then your limitation is on which models you can use. So for example, you can use the Llama 13 billion parameters that is around 26 gigabytes of RAM. Or you can use a Mixtral 4 bits, that's 22 gigabytes, but you cannot use a Mixtral that's 19 gigabytes, right? Then you also need to think about optimizing inference. So how you can batch the many requests together. You need some sort of strategy. Your strategy might be that you have no batching at all, and then you process the requests as they come in. This will give you some steady utilization of the GPU, but you won't be able to fully utilize the full power of the GPU. You can also have dynamic batching, so you can wait between the different requests and process them in groups. For example, you can do some batch requests. You can process requests every 1 hour, for example. So this is good for tasks that you don't really care when you get the answer, unless as long as you get an answer and so on. And then continuous batching is sort of something in the middle that will sort of keep the utilization of the GPU steady, but and towards the 100%. But there's some more complexities in dealing with that. Okay. The other thing that you need to decide on is on parallelism. So assuming that you have many GPUs, how are you going to use them? The first approach might be no parallelism at all. If I have 3 GPUs, I can launch 3 different models on each GPU, for example. But in doing so, if you have larger models, for example, like Llama 3, the 70 billion parameters, you might not be able to run it on a single GPU if that has, let's say, 40 gigabytes of RAM only. So if your model is 60 gigabytes, you cannot use it at all, right? The other strategy is to use some sort of pipeline parallelism. So you split the model layer by layer across GPUs, but the idea here is that only one GPU is active at each time step, right, until you finish the execution. And the other approach is using tensor parallelism. Effectively, you can split your model into several chunks. Each GPU gets a different shard and is processed separately. And the idea is that you can now utilize the GPUs at the same time, and then you can split the model, let's say, from 60 gigabytes into 30 gigabytes and 30 gigabytes, and you can process it on multiple GPUs and so on, faster and without wasting any GPU time. So this is, again, there is no right solution to that, but there is something that you need to keep in mind when you do your local deployment. And the other idea is consolidating infrastructure. So you have a central compute infrastructure, and you'll see today also in the hands-on that you can have the models deployed in some central infrastructure, and then you can build applications on top of that models by pinging the model, right? So you deploy once, and then you just maintain that. And the rest of the organization uses the models as a resource, and they can build on top of that. And this effectively increases GPU utilization. So you have this idea of the inference service. So instead of having, let's say, if you have, let's say, access to 4 GPUs, instead of launching one model on each GPU, you have some sort of inference server. You have the model central, and then the resources are all used by this inference server, and the server will decide what's given to each application, for example. So as a so there are two aspects. So you sort of decouple the infrastructure from the application, and different people are responsible for different things. So as a developer, you won't be really care about the infrastructure, but you'll be only using it as a resource. And something else that you need to have in mind, and this is, I think, ambitious as well. So build as if you're going to replace the model within 12 months. And I think 12 months is quite a lot. The landscape is sort of evolving quite rapidly. So even if you have one model that seems to perform best, let's say, if you're going to build your infrastructure around that model, then in 12 months, you'll have problem, because you'll need to change the model into the new fancy thing that works better than the previous one, and so on. And the idea here is that you should have abstractions and focus on building AI applications and not how the models will evolve, right? So your infrastructure it won't be dictated by the latest model that you have today, but you should allow some room for in case the model changes into something larger and so on. And then you can also use small models. So we're talking about large language models, but you can also have lightweight versions of these traditional models. And these are designed to operate efficiently on resource-constrained environments, right? So either smartphones, embedded systems, and so on. And these are much smaller than the typical foundational models and so on. And the idea is that they still retain their core natural language processing capabilities. So you can still use them for text generation, summarization, translation, Q&A, and so on. And there are many methods of doing that. So the three that worth mentioning is through knowledge distillation. So you have a teacher model, the foundation model, and then you have the student model, and some knowledge is transferred from the teacher to the student. You have pruning. So if you have different weights and less important parameters in your network architecture, you just sort of remove these. And then you have quantization. We already mentioned that. So instead of using high precision numerical values, you sort of convert them into lower precision, even to integers. And the benefits is that you have low compute requirements, and that translates into faster inference. You can use it on device. You have cheaper deployments. You have still the customizability and low energy consumption, and that means low electricity bill. And you can see that you have similar. So you have the Gemma 3, 4 billion. So this is a small model from the actual Gemma. You have Gwen, you have Llama 3.21 billion parameter. This is a smaller version of Llama. You have DeepSeek and so on. And then the applications are pretty much the same as the ones that you use the large language models. And the idea about that is you can sort of try it and experiment with small language models, and if they meet the requirements of your task, then it makes a lot of sense to use those instead of using a large language model that will require significant more resources. Okay. And just to summarize here, we have, if you're doing the LLM deployment, you need to figure out your deployment boundaries and then work backwards. So what sort of hardware you have available and work backwards. You should always quantize. Spend some time thinking about how you can optimize inference, either through the batching strategies or the parallelism strategies. Then you should also consolidate your infrastructure and launch the models there and provide them as a resource. Build as if you're going to replace your models within 12 months, I would say 6. And use small models when you can. Now, how you can choose the right model, that's a compromise. That's a sort of trade-off between size and performance. Usually, if you have small models, you have faster inference. And if you have larger models, you have better accuracy. So you need to find the sweet spot between those two. Now, also the task stability. What do you want to use the model for? If you want to use it for code generation, then it might make sense to find a model that is good on code generation, even though if it might not make great summaries, for example, okay? And then licensing and costs. So if these are open source or if you can use any commercial options and so on. Now, you can find many open source models from the Hugging Face ecosystem. So you can go to the webpage if I'm pretty sure many of you already did that. But you can go there and you can find the different models. You can open the model cart and you can sort of read the information about the model. You can see its size and so on. And then the idea here is that you can use those models and deploy them locally. So you have two main options that you can use for local deployment. You can use vLLM. We're going to be using it today on the final hands-on, and then Ollama. And at least to myself, the distinction on when to use each, I think it's very clear for me at least. So if you're going to deploy the LLMs on your local laptop, for example, or your desktop, I think it might be better to use Ollama, right? It's easier to use, and vLLM, you can use it for if you want to run LLMs very efficiently. So it's much more efficient compared to Ollama, especially when you try to serve multiple users in one go. So there are four main pillars that you can think of about when you want to do the local deployment: the concurrency. So vLLM usually handles multiple requests and staying steady, even with a lot of requests as they come in. We're gonna figure it out. We're gonna find out today if this is true, if you're using it multiple users at the same time. Now speed also. So for example, just to compare, a vLLM for 16 requests in one go, it took only about 9 seconds per request. Although Ollama at the same time, for the same amount of requests, it took 17 seconds. And then for 16 concurrent requests, the vLLM also produced almost 2 times as many tokens per second as Ollama. And even when we tried until 32 requests, it sort of produced 100 tokens per second quite smoothly, although Ollama started to struggle at this time. Okay, and just as a rule of thumb, you can use vLLM if multiple users are going to use these models. Ollama if you're going to use it for some personal projects and so on. Now, to start with vLLM, so first you probably need a GPU. And then first you can install it through pip, right? And then what you can do is you can start serving the model. So for example, here you can serve the model with vLLM serve, and then you select the model. And this will effectively download the model, and it will sort of make it accessible at the local URL through the port 8000. You can also change that through some different command line arguments. But the idea is you install vLLM, then you do vLLM serve, and this will sort of launch your model locally. And if you happen to use the OpenAI the OpenAI API. So this code is the same as if you were to use the OpenAI API. And what you need to change, so see, we're still using from OpenAI, import OpenAI and so on. We still use the same client, but what we change is the API key, which is going to be our actual API key, and the base URL that now points to the local instance of the model that we deployed. So the remaining of the code stays the same, okay? Also, you can have different tools for interface. You can have OpenWebUI, the Hugging Chat, anything LLM, and so on. And this is effectively the front that you'll see as a user when you try to use these local deployments. This one shows the OpenWebUI. We've also played with that ourselves, and we found it quite useful. And users are also familiar with this type of environment as well. You can also use other environments, like other fronts, such as Streamlit, for example, is also quite good. And now the economics of LLMs. If you want to do some local deployment of LLMs, you can set different price points and different depending on the capabilities you might want to your infrastructure to have. So the first one, the simplest one that we could sort of build ourselves, is one RTX Pro 6000 Blackwell GPU, 96 gigabytes of RAM. So this is quite decent. And this one effectively starts at 17,000 euros. Well, 18,000, I would say. And the price per GPU here is 8.5K euros. So this is a very good workstation that you can use for your own local deployment, and then you can sort of extend the same workstation, so the same casing, the same motherboard, with 4 NVIDIA RTX Pro 6000 Blackwells. So you'll have total of around 340 gigabytes of RAM overall. And this one now comes to 50,000 euros, right? But this is quite decent. And you can also have something similar as a system node, for example. You can have eight NVIDIA GPUs. In this case, we have Adam, but you can sort of upgrade them to the newest Blackwells as well. They only differ by 1,000 euros. And now you can have a whole server with 8 GPUs. In theory, you can use either 8 different models at the same time, or you can serve one larger model for multiple users. And this now comes to the 85,000s. And now you can also scale it further if you start using the bleeding edge GPUs such as H200 or B200 and so on. Okay, I think that one goes all the way to 300,000 euros. But those ones are much better if you want to do fine tuning, right? If you don't want to do any fine tuning, I think around these prices, you are good to go. And the main difference between the system on the left and the system on the right is that the right one, you can duplicate it and scale it with high-speed interconnects. So you can have, let's say, if you want more even more GPUs, you can have the same exactly replica of the node, n times, and you now have n times 8 GPUs. Okay. Now, the second session is about a quick introduction to RAGs. I will just mention a few things, and then they will become more clearer in the next sessions that are only about RAGs. And the idea is that if you want to influence the responses from the LLMs, there are different approaches to do that. But as you select a different approach, the complexity, the cost, and quality change. So first, you can try with different prompts. You can do better prompting, and then you can try to sort of make the model respond to what you need. This is easier to do. And then you can sort of move into RAGs. You can sort of provide extra information to the model through some database. And effectively, you need to spend some time, you increase the complexity and so on. And then you can sort of fine-tune the models as well. So you can perform a few iterations of training so that the models will be updated with your own data. And this is you're increasing complexity and cost as well. Or you can train from scratch, right? The first few you can do it on your laptop, and the last two you'll need probably a supercomputer to do them. Okay. So these are the different ways you can influence the LLMs. RAGs effectively provide you some sort of a process where you sort of, so RAG first stands for Retrieval-Augmented Generation. They provide you some mechanism in order to provide some external information to the model. But this is sort of an intelligent way of doing that. So as a user, you have some documents, you sort of put them in some database, and then your goal is to retrieve only the relevant ones and include them in the context of the LLM so that it can provide you a better response. And the main reason for using RAGs is to reduce hallucinations. So if the model won't know something, instead of saying you, I don't know, it will probably say something that it's irrelevant, wrong, but it will say it with high confidence. And effectively, this is what's hallucination. So if you ask the model, what's the capital of France, and it doesn't know for whatever reason, and it will probably say that, for example, the capital of France is Marseille, and that's it. So this is an example of a hallucinated response. A more grounded response would be the correct one, which is the Paris. Okay. And if for whatever reason the model doesn't know that, and you have some RAG in place, it will retrieve the information from the database instead of from the trained data that it has. And effectively, RAGs, they split into two phases. So first, you have the indexing phase. So you have the indexing pipeline that you start with the documents, and your goal is to extract the content, feed it into the embedder, and then create some sort of embeddings. So these are, let's say, some vectors, numerical vectors, that then you store into the vector database, right? So that's the first phase. Usually you do it once unless you have new information. Then if you have new information, you can sort of reindex that new information that came in. And how it works effectively, let's say you have the document. You have different phases of the document. You can use a context extractor, and then your goal is to effectively extract the content. So you have some text, some paragraph, you have some table, you have some other paragraph, and so on. And then you want to create from this text, you want to create the vector embeddings. So these are a numerical representation of the same text that you have extracted. So for each piece of text, you want to create these vector embeddings and then store them in the vector database. Okay. Yeah. And the idea is that this vector database will have some different vectors, and you will end up with some vectors stored in the database. And the idea is here that when you want to get a response from the LLM, you provide the user prompt. So now it goes through the embedder again. And the next step is try to retrieve any relevant information from the database that you stored earlier and include this in the context of the LLM so that it will provide the response. And the idea is you have the content and sort of you query through the embedding model. So you end up with some vector embedding. So you end up with some new vector. And then you go through the database and you perform some similarity check with the vector embedding that you just created with the ones stored in the database. And the idea is it will give you the results back, and the results will contain vectors that are similar to the input vector you have created just now. And I think Nikos has a nice example of doing that actually in practice, and let's see how that works. And the idea is, so you retrieve the vector now, and you include that in the context of the LLM, and it will provide a more informative response. Okay. So compared to the traditional LLMs, the knowledge in those LLMs is static. So it's what it acquired through training. Okay. Using RAGs now, you can have a more dynamic knowledge base through the vector database. And the traditional LLMs may hallucinate. RAGs are usually more grounded. It doesn't mean they will never hallucinate, but usually they are more grounded. And if you want to perform any updates on the traditional LLMs, then you need to sort of either retrain or perform some fine-tuning. And with RAGs, you just need to update the knowledge base. So you need to rerun the indexing phase that you have at the beginning, and then your database will be updated. And finally, the main reason that you might want to use RAGs, you can have domain-specific knowledge ingested in your LLM that you want to use, for example. Okay. Okay, and a very popular use case of LLMs are chatbots. So usually in customer support, you can ask questions about the specific company, for example. You can have it for legal research, going through the available laws and documents. For healthcare is also used. And then enterprise search. So if you want to, let's say, provide a filtering mechanism for the different policies in your company and so on, that's a very good use case of RAGs. And the elements of RAGs, so you have the data that you need to have in place, the documents that you need to index. Then you need to create some sort of database. This is a vector database. You have the interface. The interface can be the Open Web UI front that we've showed earlier. And then you have the server that will effectively run the model. So you need to also have the infrastructure that will run the models that you need for RAGs. And there are different databases that you can use. We've experimented a lot with Milvus, but there's also Pinecone, Chroma, and Dran. And then some frameworks that you can use for building your own RAGs. You can use Llama Index, LangChain, RAGflow. And today we'll be using Haystack in the final hands-on section. That was all from me. Thank you for listening. Do you have any questions before we move on with the interesting parts of today? The hands-on. Yes. No.
We basically install local LLMs and we fire them out. Not so much success. So I have a couple of questions. How easy is pay? We will pay a local LLM for better responses, basically for code generation. Because we try a few, I would say, small also hardware limitations, over trying to figure things out. So do we need to fine tune? And if we do, how easy it could be?
I think the process of fine tuning, actually the code for fine tuning the models, I think it's simple enough. The process of that, but the rest, I think it's you need to have a lot of data first of all. Well, using the data that you have, first of all, you can perform a few iterations of training. So instead of starting from 0 random weights all the way until you end up with some good weights and some good accuracy. You take the model as is trained already, and then you want to provide some data to perform a few training iterations in order to change the weights towards your data, let's say. I think you can do it with PyTorch and existing libraries as well. But the idea is you will need significant resources, computational resources. Yeah. Because, I mean, if you want to take one, let's say, for GPT-4, if you want to take, let's say, if there was a way to take GPT-4 and try to fine tune it, even just performing one epoch, first of all, you need to feed 2 trillion parameters into one machine. So first you need a lot of GPUs that will handle the capacity. If we're talking about fine tuning, we're talking about even more memory. So maybe ×2, ×3 of the memory that needs a model to run. So you need the infrastructure, but also you need a lot of data for fine tuning. I would say try and figure out, try more maybe different fine-tuned models for code generation that they're already fine-tuned there. If you go to Hugging Face, there are different models for code generation. Okay.
That's what our impression was like 3 months ago. I don't know, maybe something changed because going through for the last 6 months. And the other question, can we use small models for large systems?
Yes.
Yes.
You can use them in rack systems.
Small model like the range of 7 million parameters.
Usually they're faster. So that's what I was trying to say earlier. If you want to use some small model or even any model, I think the best way to decide if you want to use it or not is try it out for the specific task that you have in mind. And if it works good for your task, then I think it's fine, right? Even if it's 1 billion parameter, if it does the right thing for your task, then you should stick with it.
Doesn't do it. The level that we think was the way. Maybe it was fast, but we were happy, I would say, around 70%.
Okay.
So we have a local knowledge base. We tried different chunking mechanisms, embedding techniques, but still we are not very satisfied with the local, with small local. Accommodate all ourselves. And I was wondering, do we really need cloud models to a large system for the same performance for all the systems?
I mean, if you don't really care about
the open source model, the small open source model, for large systems. But in our experience, they still do not perform well.
Yeah. I mean, you need to try them out. Right? Yeah, I think the honest answer is yeah. But as I said, you shouldn't hang up too much on a specific model, because in probably 12 months, you might need to change it. Yes, I think, yeah, and have a framework in place that you sort of can evaluate them for the task that you want. Okay. I will hand over now to Nikos for his part. Nico, sorry, I stole 5 minutes from you.
No problem. It's fine.
Okay, can you see Nikos? Yes. Can you try and share?
Okay, I will share my screen. Can you view the notebook?
Yes. Can you zoom in a bit?
Yes.
Spiro, is the
Is this better or same? I cannot hear if you say something, please.
we have it. Can you get that?
Okay.
Okay, Nico, we have a bit of a trouble looking at your notebook due to the lighting here. Can you maybe try and change it into a white background instead of black?
Yes.
Also, you can join Zoom and you can see it on your screen as well if it helps.
Is this better?
I think it's better, yes. Okay, and maybe close the table of contents. I think it's better, yeah. Okay, sorry,
There's more.
just one moment.
Mhm.
So for the people that are local, Bureau will now send the link to the notebook in Zoom. There is an issue with uploading on our website, so you can find it in Zoom. So join Zoom, please, and you can find it here.
I am sharing the link on Zoom chat, right?
Yeah, Sonico, please send it on in Zoom, and we can access it from there. Okay, I'll leave you to it. If you need anything, just let me know.
Okay, thank you.
Cheers.
So good morning, I am Nikos. I'm a data scientist at GRNet. GRNet is the national infrastructure for research and technology in Greece. We operate the Greek supercomputer ARIS, and we are working on Daedalus. Most probably it will be ready on 2026. And we are the NCC of Greece, the corresponding entity for EuroCC in Greece, and we have a very strong collaboration with the Cyprus Institute in HPC AI and other projects. My part is of the presentation is a very basic introduction to RAG, to Retrieval-Augmented Generation, and actually it consists of three parts. I will start with transformers. We will see some basic function calls of the transformers library, which is perhaps the most important library for LLMs. Then we will move to embeddings, how we encode words and sentences into vector, into a numerical representation. And then we will combine the first two parts to explain RAG. We will use context in the user's queries, and we will get the responses, as Chris said previously, grounded to this context. I would prefer if we have an interactive section. This is a hands-on section, actually, so you can interrupt me, you can ask me questions, or have brief discussions after each step. I have shared in the link, in the Zoom chat, the link of the notebook. The only thing you need is a Google account. If you have Gmail, you can directly run the notebook. And also, throughout the notebook, I have an HPC in square brackets flag where you can run some more commands, and the same code, however, the same code, you can run it on an HPC environment, on a cluster. So we could present it on Colab, but the same can run it on a cluster. The first thing we need to do is we will need an environmental variable, the hidden face token. This is necessary in order to authenticate and download models. And you can generate one even now if you don't have via this URL, hidingface.com/settings/tokens. You will only need read permissions. No need for write permissions, and actually it is better to avoid any misuse of the tokens. Okay, so I will wait a bit here, and I will ask if you have a token or if you have difficulties creating one. Can you please give me a feedback in order to see if we are aligned, either from the Zoom or from the class? Let me ask it differently. Is anyone that already has a token, a hidden face token? No. The key carbon apparently is not working. Okay.
You need to.
Basically, you can start with a Colab now for this session. Can you please write me on the chat if you can view the Colab notebook and if you have a hidden face token? Colab works fine. Okay, thank you. Nice. Thank you. I have a token. Great. Okay, nice. Thank you very much for the feedback. As I said, I'm asking because I want to make it a hands-on lab. I believe it is better for your understanding. So that's why. Okay, so I will continue. We will, through this notebook, you can run any model of any hidden face model, given that you have enough compute power. So for running them on Colab, Colab gives us 16 gigabytes of GPU RAM. We will run some small models. I have indicatively here two well-known models, Mistral and Llama, but you can also run any other model. Now, I will open the link of Mistral because we will need to authenticate for the model now in order to get access. Some models are called gated on hidden face, and they need permissions. So here, if I open the link of Mistral 7 billion, you can view that it displays gated model. You have been granted access to this model. If you don't have access, you can, somewhere here, you should see some terms and then introductory text, and you can click request for access. It is a blue button. I don't remember the exact text, but it is something like that. And you can check if you indeed have access in gated repos. In hidden face, you can go in your settings, gated repositories, and you can view which models you have access. If everything is running fine, you will view there Mistral 7 billion dash instruct v0.3. This is again very important, and we need to finish this before proceeding, because if we don't have access to the model, we will have troubles downloading it. I also have Llama. Llama, the last few months, has some issues. Many users have faced some issues downloading the model. That's why I start with Mistral. If you go to community here, you can view some request for access problems. And in any case, as I said, you can go to models on Hugging Face and select any model that you want to use. The only, of course, we are talking about text generation and preferably instruct models. So, for instance, you can sort them by most downloads. Here you can get QN 7 billion. You copy the handle of the model, and you just paste it in the next cell here if you wish to use another model. Okay, this is about Hugging Face. Now, I have to ask again if you have acquired access to the Mistral model. If you see here in your gated models, if you see gated repositories, if you see Mistral 7 billion. Please write me on chat or open your microphone, whatever you like. The question is if you have access to Mistral. The link is at the beginning of the node here. And the link for the gated repos is here. If the direction is not working, you can double click on the markdown and you can copy the link. Okay, I see some people have already installed. Thank you, great. If someone has troubles getting access, please let me know to resolve it as soon as possible, because we will not proceed otherwise. Okay, nice. Okay, I will continue, and if you want, you can ask. Now, in order, it is very important to say that the tokens should always be environmental variables. We never save them on files because they are very important variables. Sorry, the repo was private for the election. So in order to make HF token experiment environmental on HPC, you will run these commands. If you see the HPC flag, you can ignore it for now, but you can run it on a cluster. These are the dependencies. For Google Colab, everything is pre-installed, actually, so the only thing we need is bits and bytes. Bits and bytes is a library for the quantization of the models here. It reduces the size of the model because we only have 16 gigabytes of RAM, so we will use less precision in order to have to need fewer GPU RAM and also to have faster models. If you have bigger compute, you can ignore bits and bytes. I have Mistral, but Llama is pending. Yes, Llama has some issues. As I said previously, if you go to the community tab, many people have issues getting access. So that's why I will start with Mistral today, but you can also download any other model, usually up to 7 billion parameters. If you go more, everything will crash. I mean, for this compute power. Okay, so let's start by installing bits and bytes. I have already installed this. Please run this cell, the first cell actually. Pip install, upgrade bits and bytes. It takes around 1 minute, something like that. And you will get the installation of the bits and bytes. Yes, these are HPC commands for the allocation of the resources. As I said, for today, you can ignore them and you can run them perhaps later. Now, having installed bits and bytes, you can proceed with the imports. We will use transformers. Transformers is the library for running and fine-tuning and training large language models. It is the golden standard now. And we also import OS, torch, time, and regular expressions. And here, on this cell, you will set your Hugging Face token as an environmental variable. If you run this cell, you will be prompted in a new input text box to give the model, and it will be stored hiddenly in your own environment. So here you run this and you set the HF token. And finally, as another preparation step, we need to set, this is not necessary, HF home is the directory for downloading the models, where the models will be stored locally. Locally, we say on Colab. And I set this specific path in order to have easy access to my model. You could skip this and you could use the default. Then I said I give here the name of the model. You can get this from here. If you click the double square button, you will copy the model and you simply paste it here. So here we set the name of the model. Yours on the class, and I don't know if this is for me. Let's discuss this in a while. Okay, yes. So my model, I set my model, and we need, in order to continue, we need to download two things. The first is the tokenizer, and the second is the model itself. If you notice, here I imported from transformers auto model for casual LM and auto tokenizer. The tokenizer will transform the inputs, which is text, which is a string, into PyTorch tensors. And we need this transformation in order for the model to be able to, let's say, understand the text. And then is the actual model that we need that we will use. Here, it will take some time. If you click these two cells, the second cell will take more time because it will download the model. It is, if I remember, around 7 gigabytes. Here, you can view the weights of the model, the safe tensors. It is more, it is almost 5 plus 4.5. It is around the total, around, it has the consolidated tensors, 14 gigabytes. And that's why it will not fit on the RAM, because we have some overheads. Colab has 16 gigabytes of RAM, so this will be very difficult to fit. And that's why we use the bits and bytes library, and we will load everything, the model in 4 bits. in fewer accuracy, in less accuracy. Do you know what to specify? Okay, I will wait here a bit for you to download the model, and please, it will take like 3 or 4 or 5 minutes. So if somebody has already downloaded the model, please write on the chat in order to know what is happening. Now I will try to answer the question. Do you know what to specify for QoS? QoS, it depends on the cluster, actually. Do I have QoS in my commands? It is the cluster partition. I don't know if I have QoS here. Let me check. QoS default, yes. Okay, this is a correct point. Actually, this implementation is for Meluxina. Meluxina is one of the Euro HPC joint undertaking supercomputers, one of the 8 biggest machines in Europe. And on Meluxina, you have various clusters, various partitions on the cluster, and here I define the default. For Cyclone, I don't remember if it has a QoS. Perhaps you can ignore this and try to run it without this command. No need to specify, it is already answered. So now I see, Chris, your response. So we say the same. Okay. Okay, so I am waiting. Yes. Can you tell me if you can view here some green bars, increasing green bars corresponding to the downloading of the model? Probably you have already downloaded the tokenizer, and you are now downloading the model. Please write on chat to be aligned. It's getting okay, green bars, nice. Thank you for the feedback. Nice. That took 12 minutes. Now, this depends on the speed of Colab, of the internet on Google Colab. Sometimes it is faster, sometimes it is not so fast. Okay, if somebody wants to ask me something till now, please open your microphone and tell me. Otherwise, I can continue with some more commands while the model is being downloaded. That's okay. So here, this is not always necessary, but some models need to specifically specify the PAD token to be equal with the EOS token. These are technical for transformers library and for the transformers architecture in general. EOS token is the end of string token, and the PAD token is the tokens that we put for the unknown, for the missing words. For instance, the transformers, in order to function in classical machine learning in a database, every instance of the dataset has the same length, has the same number of features. In natural language, we don't have this same number of features, so we have to convert them to the same number of features. And that's why we need the pad token. The missing words, we use a specific token for the missing word. And some models need to specify that the pad token is the same with the end of string token. So, okay, I mean, you can just run this command without more in-depth investigation. Then we will need a streamer. A streamer will help the model provide its response in real time because LLMs are heavy models, and perhaps it will take like half a minute or 1 minute to get the response. By using a streamer, you can get the response in real time while the model is also simultaneously processing your request, and it is very helpful for chatbots and assistants, etc. And here in this cell, I will define the messages. What I am sending to the LLM, the messages are actually a list of dictionaries from a Python perspective. You can see here the square bracket for the list and the curly bracket for the dictionary. And we start with some system instructions. We give some, this is perhaps the most important message we send to the model. This is the role of the model, what it is supposed to do. Here, I have a very generic system instructions. You are a helpful assistant. However, in many cases, especially in RAG, we need more. We need to work on the system instructions to specify a role. For instance, if you create an LLM for legal processing of legal documents, then you can tell the model, you are an experienced lawyer on commercial law, for instance. Your task is to do this and that. The first is this for RAG. The second is, it is a very good idea when we are using RAG to explicitly tell the model from the very beginning, from the system instructions, that it should adhere to the context that we will give to the model. I will make this more clear a bit later, but it is very important for us to apart from providing the context, to use some prompt engineering in order to tell the model that it should be focused on the context and not answer on its own judgment, whatever, its own knowledge. Okay, so we define the first element of the list, which is the system instructions, and then we append a second dictionary to a list. The list is my messages, dot append, and here we say role user. Previously we had role system, now we have role user. We have one more, which is the response of the LLM, role assistant. So here role user, content, my prompt. And my prompt here, I will stress a bit the model. I am asking it, explain linear regression using label. Use D as the symbol for the dependent variable, and I, capital I, as the symbol for the independent variable. D is for dependent and I for is dependent, because usually the models are using Y and X for regression in the regression equation, and we will see if it is working. We have some questions. I got this error in let me check this. I have a message here. Yes, I don't know. Does anybody else has an HTTP 401 here in the tokenizer? No. No. I'm afraid that I don't know this. Let me ask it differently. Can you, I will ask again if you can tell me if you have tokenizer and model. Some more people have had two answers previously. If the downloading of the tokenizer and the model is finished. Yes. Okay, so it is working now. Yes, okay. Okay, okay, thanks. I will proceed and we can check it out also later. So here we have our messages. Okay, actually we have a list of two dictionaries, the system instructions and the first prompt to the LLM. It's downloading, okay. It will be soon downloaded, hopefully. Now, afterwards, I remind you the tokenizer is an object. It is defined here. It is an auto tokenizer instance, an instance of this class. So we have the tokenizer. This object has a method named apply chat templates. Chat template. Here we give as an input our messages and it returns tensors. So if you run this cell, you will view in the print here that the type of the inputs now it is a PyTorch tensor. Previously it was a list of dictionaries of strings. Okay, now it is PyTorch tensors. This is very important. That's why transformers is very useful. Otherwise, I mean, it would be very hard, but you will have to do it manually. Still downloading it. Approximately what percentage it is? It is at least the half downloaded or 1%. Andreas or Panagiotis? Just finished. Okay, okay. Nice. Thanks. Yes, it takes some time because it's very important to understand that now we have the model finished. Okay. Locally in quotes on Colab, but I mean, these are not API calls. You run the model, you can run this on your laptop without internet in order to make this clear. Okay. And then I continue to moving the inputs to the GPU. And I say because we can run the model on the CPU as well. If you don't have a GPU, you can run it on a CPU. Of course, it is much more, it will be much more slow, 30%. Okay. Thanks. We wait. Okay. Okay, so here I say inputs equals input if I have a GPU, which is this well-known PyTorch command. Inputs equals inputs dot to CUDA. And I do the same for attention mask, and I print an informative message. And finally, here is the magic, where we actually call our model. I provide a maximum tokens variable. Okay, sometimes the models are very verbative and they provide very big response, so we need to stop the response. And I give the inputs, which is the PyTorch tensor, the streamer, which is the streamer object, the path token ID, I explicitly telling that it is equal to the tokenizer's the specific tokenizer I downloaded, end of string token ID, the attention mask, and the max new tokens. And I get the response. Now, if you notice here, you see they are not so much processed, the responses of the transformers library, because you can view also the system messages and the user's instructions. You see here, inst, you are a helpful assistant, explain linear regression using LaTeX, use the blah, blah, blah. And then slash inst, and here is starting the response of the model. Linear regression is a statistical method, blah, blah. This is the response of the model. Most probably you can view it in real time. Now, so actually, and now, this is the first thing that we have in the response of the model, some text that we want to remove the system instructions. I want to get a clean response. This is one thing. The second thing is that this method here returns outputs. Outputs, if you see here, is a PyTorch tensor again. We give tensor, we get tensor. So we need to convert the outputs to decode them to back to text. So we call again the tokenizer dot decode now outputs of 0. For some reason they are saved in the first element of this matrix. Okay, and I also use these variables, skip special tokens and clean up tokenization spaces in order to clean the response. And finally here I print the response. Next. Okay, I can see that, yes, oh no, it is correct. Yes, it removed the inst, etc., but it still has the instructions. And I need one more step. First of all, this is a class string now. It is string. I gave a tensor to the model. I mean, I am telling this because even if the model is streaming, what I see in my screen is not a string. Okay, it is only converted in string on the fly. The response is still tensor, a PyTorch tensor. So here I have the generated text, which is a string, but I need to clean the string in order to remove my initial prompt. So and the system messages. So I do this splitting here. I get the generated text dot split with a splitter my prompt. I get the second part from 1 to something, from 1, I don't remember why, probably it has a white space, something like that. And here I get the clean response. Now, this is for Mistral specifically. For other models, for Llama, for instance, perhaps we will need some regular expressions in order to clean the response. I have here a regular expression for the Llama as well. Let's have a look also in the model's response. We can view that the response is the linear regression equation, one. The linear regression equation is given by D, as I asked the model, equals beta plus beta 0 plus beta 1 times I plus epsilon. So it understood what I asked the model. This is very good. Other models cannot understand. So small models, I mean, cannot understand this. And of course, it is not guaranteed that it will always understand or it will always respond the same answer. And here is in plain text format. Okay, this is the first method of calling a model via streaming. Here I also measure the time, if you notice. Okay, I have T1 before the model and T2 after. So I also print the time here. And the time was 0.73 minutes. I can also call the model without streaming. For instance, LLMs is not only for a chatbot, it is also for text processing. Perhaps I have a big collection of text and I want to summarize all in a for loop, for instance. There I don't need streaming, I just want the response. So I can call the model without the streamer. It is actually the same as previously. Outputs equals model.generate. You see here the same. Outputs equal model.generate. But I skip the streamer. I remove this command and I have the simple response. I count again the time and it is much less. This is not always true. It depends on many things, on your system, on the operating system, etc. But sometimes it is helpful to just call the model and get the response. And finally, for the first part, for the transformers library, we have the pipeline object, which is a higher level abstraction of the model and of calling the basic model method, where here we just we create a pipeline object. We still need a tokenizer, but we give the model the tokenizer and the device map equals so. This is if we have many GPUs. And I get outputs equals pipe, my messages, max new tokens, etc. And I get similarly the response. Okay, I think we will continue. We have two more parts. We have embeddings and RAG. This part was for calling the transformers library. And I will wait a bit and I will ask if you have managed to download the model, if you run the first commands, or if you have any questions, etc. Chris, in the class, is everything okay? All good, nice. Okay, so I will continue with embeddings. What is embeddings? Now, embeddings is, as you know, computers can only understand, can only process numbers, and they cannot process, I mean, in the sense of numerical computation, they cannot, and training models, they cannot process strings. So we need to somehow convert our strings into a numerical representation. And now the most prevalent, basically, most probably the only way of doing this is the embeddings. Embedding is a big vector of like some hundreds of floating point numbers corresponding to the text, to each one of the words of our document. The idea is that we create embeddings such that words appearing together frequently on many contexts, on many texts, should have similar embeddings, correlated embeddings. This is the first idea, and we use to apply an optimization algorithm like word2vec, skip, gram, etc. to create embeddings. Now with transformers, with the transformers deep learning model, one of the layers of the deep learning model of the transformers is the embedding layer, and we can directly get the embeddings from there and use them for our words. So we will use this type of embeddings, and particularly another library from Hugging Face named sentence transformers, which is a particular library for embeddings. And more specifically, we will use this model. If you go on Hugging Face and view this model, it has like 89 million downloads last month. Okay, so it is a very well-known model, and I have used this model many times, and it is working very good. Okay, so I again import some libraries. Here we will need pandas and numpy also, and scikit-learn, because we will visualize some of the results of the embeddings. And if I click on this button, I will download the embeddings model. This will take some more time, fewer than previously, because if you go on files here, it is like you see kilobytes. The safe tensors are 90 megabytes, etc. So this should be much more faster. So you download the model, you will see again some green bars here, etc. And here I have a method for visualizing the correlations of the embeddings. We will see this in a while. Now, let's have some initial testing of the embeddings model. I create a list of 4 irrelevant amongst them words like reciprocal, obfuscate, hyperbolic, and tensor. I understand that they are not so semantically related. This word hyperbolic is irrelevant to obfuscate, for instance. Okay, and I encode, I use the embeddings model. The embeddings model again is an object of type sentence transformer, as we said previously, and I encode the entire list. Here I can give either a word or a list of words, or a sentence or a list of sentences. Embeddings work for words, but also for sentences. And the embeddings model can accept list of words directly, and you get correspondingly a list of word embeddings. And having the list of the word embeddings, I compute the cosine similarity of these word embeddings. The cosine similarity is a metric measuring the similarity of two vectors. It is very similar to the Pearson correlation. It is a bit different, the mathematical formulation, but it can capture well the correlations of the similarities of the embedding. So it is widely used in embeddings. And I just print then the cosine similarity. It is this matrix here. And I visualize, as I said previously, the similarities. So to make this clear, actually, I have a matrix with all of the words I gave to the model, which is reciprocal, obfuscate, hyperbolic tensor, and all the pairwise cosine similarities. Okay, the main diagonal, here in the method, I make it 0 because it would be 1 and it would destroy the visualizations. Everything else would be smaller because the correlation of one word and itself, it is 1. So here actually I put a fake 0, and we can view that the highest similarity is around 0.2 here, reciprocal with hyperbolic. Now, the values are usually from 0 to 1. We would expect perhaps something even lower than 0.2, 20%. However, because of the training algorithm of the transformers, some association of all the words exist. So that's why we have this correlation. We will view in a while for the related words. Can I get the link to the code? Yes, I will share it in the chat again. Okay, so for unrelated words, I have small correlations that is expected. And then we have related words, book, publication, and article. I run the same code, and I can view that the similarities are much higher, 0.4, 0.5, etc. So this is a first numerical indicator that the embeddings are working well, because for irrelevant words we have low similarity, and for relevant higher similarity. Now, here I will tell this very briefly. I am doing some numerical calculation. I compute the mean value of the embeddings, the standard deviation, and the norm of my embeddings. And I can view that the mean values are around 0.39, standard deviation 0.05, and norm 1. This is expected, they are normalized. And then I compute 3 random vectors with the same statistical characteristics as my embeddings, the same statistical characteristics, the same mean, the same standard deviation, the same norm. I check the response, and indeed they are approximately, of course, there. And I compute the cosine similarity of these random vectors. And I can view that the correlations here are almost 0, 0.1 at some point, etc. Why this is happening? Because it is very hard in a high dimensional space. Here we have embeddings of 384 dimensions. It is very hard to see, to randomly pick 2 vectors and to be correlated. Basically, we can say roughly that all the vectors are vertical, are perpendicular in in a very high dimension space, all random vectors. Not all. You can do it also with Python test. This is an interesting part. And then we do some funny computations here. Here I compute the similarity of the embedding of car, of the word car, and then I compute the embedding of vehicle. I add the embedding of motorcycle, and I subtract the embedding of bike, and I compute the cosine similarities of these two vectors. And I can view that it is very high, it is 70%, which is conceptually expected. We would expect that approximately the car is a vehicle plus a motorcycle minus bike. Okay, and same for Greece is Greece equals to Athens plus Italy minus Rome. Again, 68% similarity. So we can understand that embeddings work. And finally, I have I define here a list of some sentences. The first three are interrelated sentences. The data is pre-processed to remove noise and outliers. Noise and outliers are eliminated during data pre-processing, etc. And the second group, again, is relevant, but the two groups are not related almost at all. And I compute the, again, embeddings model dot encode my sentences. I compute I encode these sentences now to embeddings, and I compute the similarities. I plot them, and I compute at the top left part of the figure the first three sentences with pairwisely again have around 0.8 similarity. And similarly for the bottom right, not so high, but around 0.5, 0.4, etc. And the top right now and bottom left are 0. So, I mean, it somehow clustered the sentences. It understood that we have a cluster at the top left and at the bottom right. Okay, here we finish the second part, and we have one more for the retrieval-augmented generation. I will again wait a bit, and if you have any questions, you can open your microphone or write in the chat, etc. Okay, so having explained the transformers and the embeddings, we can now proceed with RAG. RAG actually combines an LLM and the embeddings. Okay, we import again the same libraries, no need to run them again. I have constructed the notebook such that each part can run independently, but now we already have the transformers model. It is the same as previously. And we need a text for retrieval. Here, I am giving the description of the notebook, actually, the first cell at the beginning, saying that this notebook demonstrates the use of large language models for generating text, blah, blah, blah. You can provide there any text of your own, any text that you want to process or to discuss with. Okay, so you can change this variable here. It is a very big string. You can change the text, or you can use this. So this is my context. I want to discuss with my context. Now it is only 10 lines of text, but the same general idea, not as I said, I will present a simplified version of RAG. Marius will present a more advanced library. But the general idea is the same if you have a small paragraph or if you have a very big text. Actually, we will not use RAG for such a small text because we can give it directly as a prompt or in the system instructions. So this is a toy example in order to demonstrate the basic ideas of retrieval-augmented generation. So I store this string into my text, and then I split my text with a new line as separator. In libraries, in the various libraries, we have more advanced splitters, not only per new line, we can define more advanced separators like where a chapter of a text changes, or we can handle bullet points, tables, etc. It is much more harder to work with real-world documents. However, in any case, we will need to split our text. We split our text here simply with new line, and I get my sentences. And my sentences is a list of strings, actually. I remove the tailing white spaces and the new lines, and I give this list, my sentences, to the embeddings model. Embeddings model dot encode parenthesis my sentence. And I print the shape, and I also save it in a TXT file. Just TXT is not very efficient, of course, for embeddings, but we have vector databases to store embeddings. But here we can view, this is only for demonstration, we can view if it works. We can view the first line is the embedding of the first sentence. So this is a list of 384 numbers, each line. And then the user is asking, what is this notebook about? Okay, if you ask a large language model, what is this notebook about? Most probably it will answer something irrelevant, or it will answer, what do you mean? Which node? I don't have any node. So here we will try to see if by using RAG, the model will be capable of answering this question. In order to do this, we need to encode the user's question as well. We encoded previously the sentences, and now we encode the user question. So we have the my question variable, which is what is this notebook about, embeddings model.encode my question, and I get my question embedding. If you print my question embedding, you will view again this NumPy array of numbers. Now, so we have the embeddings of the context and the embedding of the question. And now we have only 10 sentences. If I have 1 million sentences, I would need to select to pick the most relevant to my context. In order to do this, I compute the cosine similarity of my question embedding and my embeddings, all the embeddings. And I sort them by argument. I mean, compute the indices that sort the similarities. And I can see that the most related embedding is the third. We start from 0, then the 8th, etc. And here I get the sorted sentences, which is my sentences of I for I in sorted indices, and I print these sentences and the similarity to the question. So the user asked, what is this notebook about? And the more relevant chunks of my context were the notebook then illustrates how to generate text. The notebook also demonstrates. Okay, so I understand that it worked. Not very big similarity, but 47 is okay for context. And I have the sorted sentences. Now, as I said, perhaps I would have like 1 million sentences. So I should select the top relevant. And here I state number of key sentences equals 3. I just select 3 sentences. This could be 30 or whatever you like. I give the system instructions. I construct my messages. And in my prompt, I say the model now. Use the following sentences. I append the most relevant sentences up to number of key sentences, only 3. And then I say the model, answer the question, and here I put the user question. So if you see the augmented prompt, you will see, use the following sentences. The notebook then illustrates blah, 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 blah. And then answer the question, what is this notebook about? And this is hidden. We give this as a hidden text in the model, the context along with the user's question. Actually, the first part, to retrieve the retrieval part, to retrieve the most relevant questions, is some sort of a search engine. So actually, RAG combines a search engine with an LLM. And finally, I will run the model. I download again the model. We already have it. No need to run this. And I will use the pipeline object for simplicity. And I wait for the answer. What is this notebook about? And this is the final answer. This notebook is about demonstrating and illustrating text generation using a model, both in streaming, blah, blah, blah. I clean the response here. And non-streaming modes. It also explains the concept of frag. Okay, so we can see that by providing context to our model, it is capable of answering our questions. Somewhere here, my part is finished. I think I am on time, but perhaps we can have some questions if you like.
Can you hear us?
Yes, yes, now I hear.
Thank you. Can you try, we have one question here.
Hello, can you hear me? Yeah. Nico?
Yes, yes, I hear.
Yes. Okay, good. Well, my question would be, instead of using the first 3 sentences that are more similar to, well, to respond the question, is it possible to use it based on the similarity rate that we get?
Yes, yes. Actually, we use the similarity rate. Here, I select the first 3 from the sorted sentences. And the sorted sentences is my sentences of I for I in sorted indices. And the sorted indices is the arc sort of the similarities.
Okay, but in that case, if there are no information in the model, how can the model know that there are no information so that it can respond that I have no information about your question?
Yes, this is a very good point. Actually, we need to construct a more a better prompt. Usually, we do it here. Answer the here I say the model. Use the following sentences. Blah blah blah, and then answer the question. I could provide a better prompt to the model, like if the context is irrelevant to the question, please provide, I do not know. Please say I do not know. One idea is this. Another idea is that I can say, I can compute the similarities. And if the similarities is like less than 10%, I can skip, I can bypass the calling of the model, and I can just reply a predefined text. Your question is irrelevant to my context. Please try again, or I mean, whatever. I don't know if I answered.
No, thank you.
We have one
I
question.
think there is also one in the chat.
Yes. Should the center's transformer model chosen to perform embeddings be somehow related to the LLM model used? Not necessarily. We can use a different, even big companies now, like OpenAI and Google, have their own embeddings model. I can create embeddings model with a different model, and I could even use traditional embeddings with where-to-vec. The embeddings is only the retrieval. It is only a search engine. We just search inside our text for the most relevant parts of the user's question. And then the model is very important, and the embeddings in order, of course, we need to have a strong embedding model in order to get good context. But also important is the LLM in order to have a process and some sort of understanding of the text, because usually the embedding prompts, the augmented prompts, are very big prompts. So we need a capable model there. But regarding the point raised, we can use a very different model for embeddings and a very different for an LLM.
Any other questions here? No. All right. Thank you, Nikos.
Thank you, Chris.
So we're gonna have 30 minutes break now. We'll be back in 12:35. There are some beverages outside for the people on site. For the people online, after the break, we'll have a session with Marios. He will be extending what Nikos already said into using RACs now on Cyclone. So let's meet back again in 30 minutes. Thank you.
Line?
Yes.
Perfect. Thank you. So I hope that everyone has access to Cyclone. So today we'll see how to serve a model through vLLM, and then we will see a couple of RAG pipelines that increase in complexity per se. So the first thing we need to do is SSH into Cyclone. There we go. And if you type LL, you should see a directory called data edu 29. What I want you to do is type, let me clear the screen, /, data edu 29, and then launch notebook. So go ahead and run this command. Make sure you're at your home directory. Do not go into any directories. And then you should see this message right here. If we type sq-me, you'll probably see only one job, which is this one. And it will take a while to load up. The other 3 jobs that you see are actually the vLLM server running. So until everyone starts the notebook, I'll go ahead and show you the script on how to launch vLLM. So for Cyclone specifically, let me go ahead and zoom a bit. Right. I don't know. Is it better? What about this? Default. I don't know if I have a white. Ah, there we go. All right. Okay, perfect. Sorry about that. All right, so this is the script. By the way, all the scripts and notebooks will be available on the GitHub after the training event. So this is the script that launches the LLM that we will talk to. And at the beginning of the script, we have basically the configuration for Cyclone, what the resources that we are requesting. So for our LLM, we need 2 GPUs and 20 CPU cores. And basically, we will launch one task on a single node. For today, we will use only one node, which has 4 GPUs. 2 of them will be used by the LLM. The other will be used for the embedder, and the other will be used for the re-ranker, which we will see at the last notebook. Either way, this is basically the configuration. Then we have to activate the virtual environment for vLLM. This output file is needed so the notebooks can actually talk to vLLM. We need a host name. We need a random port. This is the directory that we will download the Hugging Face model. This is the model that we will be using, Llama 3.08 billion is track model. You can use any Hugging Face model that you want. The tensor parallel size is a parameter of vLLM that lets you use parallelism. So if you have multiple GPUs, you can utilize all of them. So we tell it to basically use the GPUs that we allocated above, which is 2. This is for some logging. And then we need an API key. Now the API key might look silly, but it's internal, so it doesn't really matter. And at the end of the day, this is the output that we will have. So the notebooks will be able to connect. So again, we have the port, we have the host, the URL, and the API key, and the model name. We will see these parameters in the notebook. So finally, what we have is vLLM serve, the model that we want to serve, the task of the model, which is to generate text. Again, the parallel size, we see it's our GPU number, some other miscellaneous parameters, the data type of the model, I limited the model's length, so it will be easier for a lot of users to try it out, so we don't request a lot of resources from Cyclone. It doesn't matter for our use case today because the data set is really small. And finally, we expose the API key, host, and port. So all three scripts are pretty similar, except we are changing the model name and some model parameters here. The same for the re-ranker. And once we have every script ready, we can go ahead and run it. And you will see all the jobs running here. So each one of these is serving, it's a vLLM server, basically. Yeah. For some models, yes, you need to request access for the model. Like for Llama 3.0 8 billion, you need to request access from the owner's repository. All right, so the Jupyter job, now it's ready. This is that's why it says R here, and here it was configuring basically. So if anyone else doesn't see the R at their job, give it a little while. If you do have the R here, that means it's ready. And if you look into your repository again, typing LL, you should see a directory called RAG training. So I'll go ahead and go into this directory. I want you to follow along, and I'll take a small pause here so anyone can catch up. Is everyone here fine so far? Nice. And anyone online? So we'll take a 3-minute break so everyone can catch up. Perfect. I see from people online that the job is running. All right, I will continue, and we can come back to it if anyone else is having problems. So while you're inside the RAG training directory, I want you to type LL again, and you should see connection info.txt. All right, so this is important. What we want to do is type cat connection info.txt, and you'll see this output right here. So we can see 3 things here. Basically, to access Cyclone from your computer, we need to establish a tunnel with this command. So I need you to copy it and open a separate terminal that's not connected on Cyclone. So as you can see, the terminal I opened now, it's on my computer. And I want you to type that command in and hit enter. This command will not output anything, and it will stay running like that. That's normal. So once again, cat connection info.txt while you're inside RAG training. And then you copy this command right here and paste it into a separate terminal on your system. So once you do that, you need to copy the password for the notebook. And then what you need to do is open your browser and copy this URL right here. and it should open the Jupyter server right here, asking for a password. Go ahead and type the password. And you should have access to all the notebooks that we will be using today. So I'll go over it one more time. So what you need to do is you need to be inside the RAG training directory that is found under your home directory. Then you should type cat connection info doc.txt, and you'll see this information right here. Go ahead and copy this command, open a new terminal that's not connected on Cyclone, paste the command right here, and nothing else should happen. It should stay like that, don't worry about it. And after that, you need to copy your password, and then open this URL and paste your password, and you should be good to go. I'll wait a few minutes. Yeah. If some people are having connection refused error when they type SSH, make sure that the sq command --me shows R right here and not CF. And if it shows CF, that means that the job did not start yet. So this information right here won't be accurate. So what you need to do is once you see that this is R, then you go ahead and type cat connection to get them the refreshed information that will work. Give us a few more minutes so everyone can catch up, and we'll start with the first notebook. All right, everyone, sorry for the delay. All right, so now that we have access to our Jupyter server, let's go ahead and open the first notebook called RAG Basic 01. And I want everyone to make sure that on the top right corner, you see RAG Training VNV. If you don't see it, I need you to click on it. And right here, select RAG Training VNV and set it to always start the preferred kernel and then click select. Perfect. So in this notebook, we will start with the very basics. First, a small introduction to Haystack. Basically, Haystack, it's an AI framework that you can create RAG applications, agentic applications, generally anything that has to do with LLMs, you can do with Haystack. It's a fairly new framework, and that's generally good because it's not that bloated. You can see the website here. It's fully open sourced, and it integrates with many more frameworks that will be useful down the line. So the first step we need to do is actually import our packages. This will take a while. Don't worry about this warning. So let's initialize some helper functions, and then we will we will establish our LLM config. This config, if we actually look into it, it basically contains all the connection info for our LLM. So then we will see an introduction on the Haystack document data class. So this data class basically contains all our documents, their content, some metadata, some scores, their embeddings, their sparse embeddings. It contains basically various information about the documents that we want to perform RAG on. So here we have a directory that contains our documents, and we use a converter which is found in the helper function. Basically, we use a converter from Haystack, which converts docx documents to Haystack documents. So, and for the document store, we will not use a vector database yet. We will just store the documents in the system's memory. So let's go and run this. All right. And we can see, we can check what the document looks like. So first of all, as you can tell, the type, it's basically a document data class, and it has a unique ID. This is the content of our document. Basically, the documents for this training event, it's like various policies of a company, some events. Basically, imagine that your company has a chatbot and you want to talk to it. So this document, it's about the company hackathon, apparently. And you can see all the content right here. This is stored again in the documents data class. We can see some metadata again that's automatically generated from Haystack. So you can see the author, then the file path, some information about when it was created, who modified it last, and so on and so on. So now that we have our documents, we have the converter ready, we need to start indexing those documents. If you remember from Chris' presentation, this is the first step. You have the documents, you extract some content from those documents, which is the text, and then you create some embeddings, and then you store them in a vector database. In our case, we won't do that yet. So, but before we index our documents, we have to split them in chunks. And then there are various reasons on why it's that. The first reason is that our models have a limited capacity on how much data they can process. So if we have a very, very long document, it might exceed that context window and throw an error. The other reason is that, let's imagine that we have a document that spans 35 pages, but the relevant information that we want from our query, it's found only on page 5. So why load the whole document to the LLM with useless information instead of loading the most relevant chunk? And of course, this, again, we can expand this this argument by saying, okay, let's imagine that to answer our query, the LLM has to access a lot of documents. So what I'm trying to say is making splitting the documents into smaller chunks is more efficient, and it also helps reducing hallucinations because you don't feed the LLM with useless information. The goal of the LLM is to answer the user's query. So let's play a bit with the tokenizers. So right here, we will use a tokenizer from the pre-trained model BGE M3. And we will calculate the tokens for the first document, and we will calculate the tokens for the first 500 characters, basically. So you can see the token count, it's 125, and you can actually see the tokens themselves. You can observe that some words get split, like hackathon gets split to hack-a-thon. And let's say we want to see the whole document, how many tokens it has. Let's place -1 there. So the whole token is 1,200 tokens. So if our embedding model had a max capacity of 512, we wouldn't be able to load this document into it. So this is the first reason on why we chunk our documents. So another thing you want to consider is, now let's use a different tokenizer from this model right here. Let's calculate again the tokens for the 500 characters from the first tokenizer. We get 125 tokens. Now let's tokenize the same content with the other tokenizer, and you can see the token count is different. This is because each tokenizer uses different tokenization methods. You can see on the second tokenizer, the words get split differently. So for hackathon, this time we have hack-ath-on. And also, when it splits the word, the character of the split, it's different. And let's try to tokenize the whole document for the second tokenizer as well. And you can see this warning right here. So this warning basically tells us that the maximum sequence length for this model right here, basically, it's 512, but the document we are trying to tokenize, it's more. So basically it's telling, if you run this through the model, it won't go well. So the main takeaway from this is, if you are going to use a tokenizer, use the tokenizer that was used for the model, for the embedding model that you are planning to run. So let's initialize the document splitter. We actually initialized it above. Let's run the document splitter. And for this notebook, we will, hello. Okay, my notebook, it's a bit, okay, it's running, sorry. So what we see right here, first, we split the documents into chunks. And then, like I said, for this notebook, we will be serving only the LLM with vLLM. So our embedding model, the dog embedder right here, it's actually running inference using Torch, which is very inefficient and slow compared to vLLM. And you can see here that the inference time took 7 seconds, 7 seconds basically. And we stored 400 documents. Now, when we say documents, we mean document chunks. So we calculate the docs with the embeddings on this step right here. And then we write the documents to our documents store. Now we can access these documents. Then we can initialize our RAG pipeline. So specifically, we have a prompt template, to be precise. We can check the prompt template right here. As you can see, it has a task, it has some guidelines, and it has some added information right here. So when you send a query to an LLM using this pipeline right here, it will first read the task, then it will read these pipelines guidelines here, then it will read the conversation history, then the actual source context, which is basically our documents. Then it will read the user query before answering. So the components that we need to run this RAG pipeline, it's basically a text embedder. Like I said, when we send a prompt, a query to the LLM, we need to turn it into an embedding. This is how we calculate the similarity with the stored embeddings. So let me go ahead and, whoop. So yeah, we need a text embedder to actually calculate the embeddings. We need a retriever, which will basically retrieve relevant documents from our document store based on our query. Then we need a chat generator, which is basically our LLM. And you can see here for the LLM, we are using, vLLM basically uses an OpenAI compatible API key. So we can use Haystack's OpenAI chat generator method, but instead of putting the API key and base URL of OpenAI, we can put the API key and URL of vLLM. So with this code right here, we can talk to vLLM. Then we have the prompt builder. Basically, it creates the prompt for the LLM. And then we can establish our actual RAG pipeline. When we establish the pipeline, we can add the components like the text embedder, the retriever, the builder, and the LLM. And then we have to define the outputs and inputs of each component. So the text embedder will output embeddings, so the embeddings of our query. The retriever will take those query embeddings and output the relevant retrieved documents, and it will send them to the prompt builder as documents, and the prompt builder will output a prompt, and it will send that prompt to the LLM as a message. Yep. Cosine similarity, that's how it decides. But yeah, it basically, it's, where is it? Whoop. Oh, here it is. So the retrieval will basically perform this. The content, which is our documents, and the query get turned into vector embeddings. The content is actually stored in the vector database, not the query. So the retrieval will retrieve some relevant documents from the vector database and send it back to the application. Oh, yeah. So what's happening here, basically, this is an example of what's going on. We have the content here, which is our document chunks, and they go through the embedding model, and they are turned into vector embeddings, and they are stored into the vector database. So when a query comes in, it will pass through the embedding model again. It will get turned into a vector embedding, and the vector embedding of the query will get, the retrieval will basically calculate a cosine similarity between the vector embedding of the query and the stored embeddings that we have in the vector database. And the query result is basically the retrieved documents. So this is what happens here. The text embedder is calculating the embeddings of the query, and the retrieval will retrieve documents based on how similar these documents are to the query. Yeah. Hmm? Yes. Okay. No, you don't have to re-embed everything if you want to add to the vector database. Basically, a vector database, you can run SQL commands. So you can have an SQL command that retrieves the already embedded documents, and you can add the new ones to a list and embed only those, basically, and add them to the vector database. No, no. One key thing here is that you always have to use the same embedder that you used in the indexing phase. So this embedder has to be the same embedder that you used when you indexed your documents. This is because you want the embeddings to fall into the same vector space or so. You want them to be similar in structure, I guess, something like that. Anyway, feel free to ask any questions, by the way. Now that we have the pipeline ready, we can come down below. This is an overview of the documents that we have in the document store. So we have like a document about the new office layout plan, some product documents, and so on. And we can ask a question to the LLM. And we will get back a response. Now, the question was, I'm a new employee, onboard me about the Quantum Stream product, when we get all that. This is all fictional, by the way. ChatGPT generated the documents. So this is it about the first notebook. It's the second notebook will be pretty similar, but the main difference is this time we will be using the embedder from vLLM. So now we are serving two models instead of one. We will play more with the LLMs at a later notebook. So if you want, go ahead and open the next notebook, RAG Basic 02. Like I said, let's import the packages. Let's import some helper functions. And this time we're loading the LLM config and the embedding config. It does take a while to load the packages. So similarly to before, we have the documents. We convert them into Haystack documents. We initialize the splitter and we initialize the document store. Again, we are not using a vector database. The vector database will come at the next notebook. But you can see from here that this time the doc embedder, it's initialized by using the OpenAI document embedder method from Haystack. And similarly to the vLLM on the last notebook, we define an API key, an embed URL, and a model name. So let's go ahead and run this. Again, we can see some, if we run the cell below, we can see some content of our documents like before. We can check the tokens as well, but this time we will see why splitting the documents is important. So the token count for the whole document, let me change to -1, is again 1203. Now, if we split the documents by running the splitter and checking the chunk, we can see The splitter adds a few keys here. First of all, we can see the file name. Again, we can see the metadata, how many pages, and where does the split end and start. If we change the chunk index to like 3, you can see that the file path is the same. This is because this document right here, the annual hackathon announcement document, was split into multiple chunks. I'm not sure how many. Let's put like 15 here. It's still the same document. So we have a lot of chunks for this particular document. And we can calculate the tokens. The token count for this particular chunk, it's 31 tokens. Now we can go ahead and run the indexing phase again. And this time, instead of 7 seconds, it took 2 seconds to calculate all the embeddings for 400 document chunks. And this is by only running on a single GPU. You can see that the difference is it's very big and it scales up, especially if you have 1,000 or millions of documents and very large documents. So similarly to before, we establish the RAG template, that it's the exact same template from the last notebook. We use, again, the text embedder is now established through vLLM. So now you can see we have 2 models here instead of 1 that use vLLM. Let's go ahead and use this. All good. And now we can again run a few queries. And again, we get back a response. Now, I have, how much time do I have? 1 hour, perfect. Let's go to the next notebook. All right. Now let's check the vector databases. Also, let me try to hide the floating things. Nice. So now let's utilize a vector database. For this notebook, we will use the Milvus vector database. We used it on various projects and it's really good. Let's import the packages again. Let's run a few helper functions. Let's set up the vLLM connection parameters. And now let me zoom in. Now we initialize the vector database. So what we need here, basically a connection argument, which is basically where it will download the. Okay, let me start from the beginning. Milvus has 2 modes, let's say. You can run Milvus Lite, which is like this. You install it with pip install and it's ready to go. Or you can run Milvus in distributed version. So you can run Milvus on Cyclone, for example, and you can have it process thousands and millions of documents. For our use case, we will use the Lite version, and because it's not hosted anywhere, it will basically create a .db file in your directory. And this is where the documents will be stored when you index them. So this is what we put in the URI here. Yeah. It's the vector database. It's what stores the documents. You can retrieve documents through Milvus. You run indexing. Yeah. You can check Milvus. This is the website for Milvus, basically. And again, this is open sourced as well. So let's initialize our document store with Milvus document store. Again, this is an integration of Haystack. I'm not sure if this is a warning, so it should be good. All right, let's go to the indexing components. Again, we have our documents, and we have the doc embedder like before, and the splitter. Let's go ahead and initialize them as well. And now we have the indexing pipeline. And now we have a few more components here. First of all, we have the converter. We did have the converter before as well, but this time we are not running it separately. We are running it inside the pipeline, and this is why you see it here. Then we have the document cleaner, which basically does what it says. It removes extra white spaces. It removes duplicate headings, white lines, empty lines. It does some basic cleaning. Then we have the splitter that we saw before, the document embedder, and the document writer. So let's go ahead and run this pipeline. So we calculated 397 document chunks. This is the total tokens that we generated. And now everything is saved inside our vector database. So now that we have this vector database, we can test the retrieval. So again, every prompt has to turn into an embedding. So right here, we have a dummy text embedder that uses vLLM. And we have this question: tell me a bit about quantum stream. And we have a Milvus embedding retriever that will retrieve the 3 most similar documents. So if we run this, you can see the 3 chunks that it returned. So remember, we asked it something about quantum stream, and the document chunks that we got before are all relevant about quantum stream. So this is how the retrieval basically works. This cell right here is basically this right here. All right, so now that we saw how the retrieval works, let's initialize our RAG pipeline. Again, we have a prompt template, and then we have the components. We have the chat generator, which is basically the LLM, and the text embedder, like before. And this time the retriever changed as well. Now it's a Milvus embedding retriever instead of in-memory embedding retriever, or whatever it's called. So let's initialize the pipeline, and let's perform some RAG. Here we go. So again, everything works together. It retrieves relevant information. Again, this is subjective to your data and how you process your data. If you have data that's very complex and unstructured, you might need to pre-process it a bit more, which we will see in the next notebook. Let's go ahead and try the new notebook, the next notebook right now. But first, what I want you to do, I want you to click on kernel. This is very important because it will break Milvus if you don't. I want you to click on kernel, and I want you to restart the kernel. The reason is when we initialize Milvus right here, in the next notebook that we will use, we will have the same code. So when we try to initialize another document store with the same URI right here, it will basically throw an error telling us that there's already an open connection to that database. So we restart the notebook, so we break that connection. So let's close everything and get to the advanced notebook. All right. So in this notebook, we will add a few more features, let's say, to our RAG pipeline. And by the way, every single code that we will see here, it's what's running on Open Web UI, which I will show later on. This is hosted here at the Cyprus Institute. So basically what we will do in this notebook is, of course, import our packages. Let's import some helper functions as well. And now we have 3 models that we will serve with vLLM. We have the actual LLM, we have the embedding model, and now we have a re-ranker. The re-ranker, I will keep it short because we don't want to run out of time. The re-ranker does this. So we have a retriever that retrieves documents. Let's say that the retriever retrieved these relevant documents. But because the retriever works on cosine similarity and it works on the embeddings, there's always a bit of information loss. So what the re-ranker does, it takes these 25 documents and re-ranks them and outputs the most relevant, in this case, the top 4 most relevant tokens. This is very useful because you're boosting the quality of the information that you pass into the LLM. And also, you don't have to load 25 documents here into the LLM. You can load 4, which in some cases might be enough. So you don't need that, you don't use that much context. Anyway, we'll see it in the notebook as well. And the other thing that I will introduce you to, it's called DocLink. This is, of course, another open source framework. It's basically a document parser. Wrong link. So this is a content extraction framework, basically. What it does, it works with multiple file formats like PDFs, HTML5 files, Word document files, and it outputs their content in a structured way, and it also performs chunking for us. So let's test it out. Let's run this cell to load our files. And what we will do, it's called hybrid chunking from DocLink. Basically, the chunking method works in 2 steps. DocLink will first analyze the structure of the document and perform chunking on that. And then it will take it a step further, and it will use a tokenizer to split the chunks even more using the tokenizer. What this means is that if you have a paragraph and you want to chunk it, using a tokenizer, it will make sure that the paragraph won't get split in half. So all of your chunks are a bit more cohesive. So let's go ahead and test it out. We initialize the embedding model, which is something I forgot to do. I forgot to run this one, sorry. So make sure to load the connection parameters, run the cells again. Nice. So what we have here is, again, the docklink converter. And for the chunking parameter, we use a hybrid chunker with the tokenizer from our embedding model. And for the documents, we won't run it on our documents. We will actually input a URL. This might take a bit to run, at least for the first time, because it downloads a couple of models on its own, because it performs OCR as well. So it needs to download these models. Let's give it a while. This is an opportunity to ask any questions if you want. This is a warning because docklink was updated recently and they forgot to remove this argument, but they did add the check to say that it's depreciated, so feel free to ignore it. And now let's inspect a chunk. You can change the ID here, but let's check the chunk with ID 2. And we can see all of this was done automatically by docklink. We can see the heading. We can see the content, of course. And we can see some metadata. We can see that this is a text. We can see that it's a part of the body. We can see that it doesn't have any children. We can see the page number, the bounding box on the PDF, the character span. Basically, we can see a lot of metadata that can be useful to the LLM sometimes. For example, we can pass this metadata to the LLM, and the LLM, when it references a chunk, it will know which chunk, which file, which page. So basically, it can write citations for you. All right, so let's establish our vector database again. This is the same warning than before. If you get an error here, you have to go back to the vector database notebook and restart the notebook. And then we will establish our indexing pipeline like before, but this time it's a lot smaller and simpler. We have the doc embedder, and then we only have 3 components now instead of 5. We have the converter, which is docklink, the embedder, and the writer. We don't have the cleaner, we don't have the splitter, and this is because docklink will handle all that on its own. And you can see here, for the docklink converter, we have max tokens 256. This doesn't mean that every chunk will be 256 tokens. It's an upper limit. Some chunks might be 60 tokens, some chunks might be 200 tokens. But the max limit will be 256. So let's run the pipeline to index our documents. And now, instead of having 400 document chunks, we have only 59. The prompt tokens are, I think, are around the same. And now we can continue. Not sure what this. Okay, I ran the cell by mistake again. Ignore this error. Let's go basic arguments for our LLM. So another feature that we will use in these RAG pipelines is it's a query rephrase LLM. So for your RAG application, you have the LLM that you send queries, but you can have smaller LLMs performing smaller tasks. In this case, we have a query rephrase model that will take the query of the user and try to rephrase it in a way that provides more context to the actual LLM. And the task for the query rephrase is this. You are given a user query and the conversation history, and your job is to rephrase the query only if necessary following these rules. And we have some guidelines, and similarly to before, it needs the conversation history and the user history query, and then it will output the final query. So because we have another LLM, we need another prompt builder as well. Then we need the actual query rephrase LLM that will perform the rephrasing. This is a helper function to help us link the connections for each component. Again, we have the text embedder like before. We have the retriever like before. And now we have the ranker that I explained earlier. Then we have another prompt builder for the final LLM, the actual LLM. And then we have a couple of components that control the conversation history, basically the memory of the LLM. So let's go ahead and initialize all our models and initialize the re-ranker as well. And then we will initialize the pipeline. So again, for the pipeline, we have the prompt builder, the query rephrase LLM, the text embedder, the retriever, the re-ranker, everything that I mentioned so far. You can see that the pipeline gets quite large. And then we have to connect the inputs and the outputs of each component right here. So let's go ahead and run this. And all good. Ignore this warning. So finally, we can start talking to our LLM. So because now we have the conversation history and there are a lot of users, in order to avoid draining too many resources of Cyclone, I have the memory to store only 4 messages. So let's go again and run this question right here. Let's give it a while. So the question was, I am a new employee at the company, onboard me about the Quantum Stream product. And the search query, it's the same. So the query rephrase LLM did not change anything because the prompt itself was fine. It didn't need any changing. It didn't contain any typos. And if we go a bit below, we can see the re-ranked documents. So we can see the scores. For the first document, the score is like 32%, and this is the content. Feel free to look around, change the index here to look at the values. All right, don't go above 5. To look at the values, oh yeah, because I have it to retrieve the top 5, so 4 is the last index. And you can see the last retrieved document only has 10% similarity. Oops. All right, I just closed my notebook. So we can go ahead and ask something else. So let's say that we are an employee and we want to ask, do I have to attend to the hackathon event? Let's go ahead and run it. Blah, blah. It's saying something. Basically, let me go ahead and reset the memory. All right. So now we asked it if we want to attend the hackathon event, and because it is now stored in its memory, we can go ahead and ask it, will I get any penalties if I don't attend? And now it should make the correlation that we are talking about the hackathon. Yep. And also, you can see I have a minor typo here. I'm missing an apostrophe, and the LLM did add that. You can go ahead and play with it, run a few prompts. The list of the documents, it's up here. So you can ask, you can play a bit and ask any questions if you want. This is the last notebook, by the way. So we have a bit of time for discussion. And also for anyone online, feel free to ask as well. And again, all this code and the vLLM scripts and the notebook that Nikos showed at the beginning, all will be inside the Git repository that we shared, and we will share it again. Yeah, of course. Yeah. Mm-hmm. So everything that we showed today will be uploaded to the GitHub repository. Since we have a bit of time, I can go ahead and show you Open Web UI. This is, again, an open source interface that you can use it to talk with LLMs and perform RAG. And the exact code that I showed you on the last notebook is what it's running behind this HR assistant. You can select a lot of models, especially if you have an OpenAI API key, you have access to all their models. But in our case, we are using a custom RAG pipeline, and we can start talking to the LLM. It is a bit slow. It's a prototype. So here, we can ask it, we can ask it about the new office layout and if we're losing our desks. And it should hopefully answer correctly. And again, at the backend, all the code that's running, it's what I showed a few minutes ago. We are using Milvus, we are using a re-ranker, we are using a query rephraser. And this is another feature that I showed. We are telling the LLM in the RAG template to also cite which documents it's taking information for. The reason that chapter and page is not available, it's because it's how I created the documents. but generally it's working. So you can see this information comes from this document, same here. So you can have citations. And it works really well. The user experience, it's pretty similar to ChatGPT, the interface, I mean. You have all your chats, you have some settings, you have a profile, you have a lot of features, basically. It can be a training event on its own. But yeah, this is it from me. If you have any questions, feel free to ask. And thank you for coming. Please, do you have any questions online? No, this is an internal tool for prototyping and playing around. Yeah. Like a hardware architecture. For the hardware, what dictates your hardware? It's first of all your budget, obviously, and then what models you need to run. For example, the new open weight models from OpenAI require, I think, CUDA Compute 9. So you need a fairly new-ish GPU architecture. If you have like a V100, you cannot run those models. And also depends on how large your models are. If you want to run very large models, you need to go with GPUs that are more on the higher end. Yeah. Yes. Yes. Mm-hmm. Exactly. Sometimes yes, sometimes no. It depends. Milvus is just the vector database. It doesn't control the chunking. What controls the chunking is, let me go up. No, it's the Docklink converter. Yes. So the Docklink yes. So sort of. You can put a hard limit, which is 256 in this case. So no chunk will go above that, but the size of the chunks themselves, you can't really control that easily, because for some chunks, it might make sense to be 60 tokens, because let's say it's a small sentence. So you want to chunk that sentence only. For other chunk that it's a paragraph, you might want it to include that paragraph into a chunk. So it might be 130 tokens. So this is the reason we use the hybrid chunker. So it's basically this right here. The content extractor, which is Docklink in this case, will first find the sections of the document. So a paragraph, some tables, another paragraph, which is this. And then it will take each one of them and chunk them even further using a tokenizer. So this paragraph might be split into 3 chunks, let's say. Mm-hmm. Yes, if you use hybrid chunking, it basically ensures that the chunks will be concise and consistent in terms of what information they contain, because you won't have a chunk that it's split in the middle. So you have a sentence split in the middle and the rest of the sentence it's in another chunk. So in this case, if it was like this, you wouldn't. Yes, but at the first stage, yes. And this is why we perform token-aware split. What do you mean by the first? It's 2 stages, but the final output it's this. Yeah, this is what will get stored into your vector database, the red part. This is just internal to Docklink. Yes, imagine it in steps of the process, basically. But at the end of the day, this is what you will get. So in the case that you have a paragraph or a sentence that gets split in the middle into 2 different chunks, when you want to load that sentence because it contains relevant information, you need to load 2 chunks instead of 1. So that's inefficient. So that's the main reason why you would use a hybrid chunker. And for the re-ranking part that I mentioned before, basically, when you first, let me see if I can find it right here. So this right here, it's the first retrieval part here with cosine similarity, just a similarity between numbers, basically. So because it is between it's between numbers, it's very easy computationally. It's not that hard. This is why you can retrieve a lot of documents, 25, let's say. But because it's when you turn a text into an embedding, there's a bit of information loss because you compress the text, the semantic meaning of that text into a specific dimensional vector. So when you retrieve these documents using cosine similarity, the retrieval may also retrieve documents that are not that similar. And also the most similar documents might end up down below because of how the embeddings were calculated. So what you want to do, also, let's say that your model cannot handle 25 documents. So what the re-ranker does, it takes those 25 documents and semantically re-ranks them again. It's a heavy operation, computationally heavy, but you make up for it in the end by giving your LLM more clear context. It's not that useless information that might come through. But again, the general rule of thumb, you start small from our basic pipelines and add to it, because at the end of the day, you might not need a query rephrase LLM, a re-ranker, a hybrid chunker, and all this fancy stuff. You don't have to go straight to the advanced. You go slowly. Yeah. If the SSH command asks for a password instead of a passphrase, that means that something happened with the SSH key. Yeah. Oh yeah. What you can do is you can put on the SSH command, you can put -i and put the actual private key there, the path. Oh. Generally, when we do these training events, we dedicate 30 minutes at the start of the event so everyone can sort these issues out. I guess what you can do if you don't have access to Cyclone, you can use these notebooks on Google Colab that gives you access to a GPU. But of course, you won't have the vLLM running. But in reality, you don't really need it for this kind of, for these notebooks at least. Yeah, but those notebooks, I think, required an OpenAI key. But yeah, we have another repository that has some RAG notebooks. You can run those on Google Colab as well. I will put the link in the repository of this training event. But for that event, you need an OpenAI API key. Yeah. So if no one else has any questions, I'm not sure. Let me check online real quick. Yeah, of course. Yeah. No, the split happens using a tokenizer, basically. That's defined by the tokenizer. Oh. Sorry? But are you talking about this Dockling split? It will split the chunk. So we have this right here, let's say. It will use the tokenizer to actually tokenize this whole thing. And how exactly it will decide where to split and what, I'm not quite sure. But yeah, at the end of the day, what Dockling does, when it finishes with all the chunking, it will go over all the chunks and actually modify them in some way to make bigger chunks smaller, to fit our defined size, and to make smaller chunks a bit bigger so we don't have a lot of small chunks, which also can be inefficient. Yeah, in some way, yeah. 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 Generally, you want to use the tokenizer that was used for your embedding model. So the tokenization of the chunks, it's what was your embedding model was trained on. So the input of the data, it's similar. Generally, you start with the tokenizer that your model was trained on, but that's not a hard limitation. You can try a different tokenizer. It probably won't make a big difference. Depends on your data, of course. if you would like to run this code again, you won't have access to Cyclone after a while. So if you are going to run it on Google Colab or your personal computer, you will have to change the code a bit here, because when it's going to run this code, it won't be able to access this API key and embedding URL. So you will either replace this method, the OpenAI document embedder, replace it with something else, a different embedder. So if you go to Haystack document embedders, you can see we have an embedder for Amazon Bedrock if you're using AWS. We have Azure OpenAI if you're using Azure. There's probably a Hugging Face API document embedder if you're using Hugging Face. So go into Haystack and read the documentation. But at the end of the day, if you're going to use this code on Google Colab, you will have to change the document embedder and any other LLM or the re-ranker. Basically, any connection that you see that points to vLLM, you'll have to change it. Unless you launch vLLM on your computer, which is technically possible. I mean, it's not something heavy. And what else? If you do have an OpenAI API key, you can leave this method right here, the OpenAI document embedder, and just change the API key here. So that will work. But yeah, Haystack has integrations with a lot of very known frameworks. For connections as well with GitHub, so you can grab files from GitHub with classifiers. You can build agents with Haystack. It's a great framework. All right. If that's all, thank you, everyone. Feel free to send me an email if you have any questions, or if you're here, find me outside and we'll have a talk. Again, thank you for coming, and have a lovely day.
All the recordings of the event, they are published under our YouTube channel. I think it's called Castor C. Yeah, if you type Castor C in YouTube, you will find the presentation, the presentations.
Yes, yes, it will be uploaded.